So thank you for letting us present on our project today. It's on using AI and machine learning to extract data from Japanese American confinement site records. This is part of a project that's funded by the National Park Service Japanese American Confinement Sites, or JACS, grant program. And it is being run through the Bancroft Library at UC Berkeley. Next slide, please. So my name is Mary Elings. I'm the interim deputy director at the Bancroft Library, and I am the principal investigator on this grant. I'm joined today by Marissa Friedman, who's the digital project archivist at the Bancroft, who's managing the work on the project, and Cameron Ford, who's the co-founder of Doxie.AI, which is a company formed by former UC Berkeley iSchool data science students. And he's here to talk about the machine learning work that we're doing with them. Next slide. So I conceived this project in 2018 to be somewhat different from my previous 4 JACS program grants, in which we were essentially digitizing, publishing, and presenting archival records related to the internment. In this project, I wanted to go a step further by exploring how we could improve the extraction of the data held in these records, with a broader goal of facilitating efficient and cost-effective data extraction across our digitized and born digital archival records, to support and encourage computational research across our collections. So our goals in this project were fourfold. First, we're creating a preservation quality image of unique resources in our collections and preserving those for the long term. Second, we are also creating a data set of the information held in those records to build a more accurate and more complete data set of Japanese American incarcerees during World War II, which improves upon the errors and gaps in the existing data file, which was originally created in the 1960s by the Bancroft Library from computer punch cards. Our third goal is that we're also working to engage with community stakeholders and representatives to guide our ethical and responsible access planning. So we're using a co-curation model with community members to talk about access to sensitive data held in the records that are held by the Bancroft Library. And then finally, our hope is to implement new methods to expand computational access to our digital special collections in line with the collections' data workflows, which encourage computational use of digital and born digital collections and supports ethical access to collections and data that we as libraries steward. So this work is really about a technical question, but also a legal and ethical one. So using machine learning to efficiently and effectively extract data from our digital archival collections has proven to be a really valuable proposition that we plan to take forward. But as we also consider the individuals impacted by or represented in the data we're extracting, this is also a critical aspect of making our data available, which is something we'll be exploring this coming spring when we hold our first community advisory group meeting with our partners at Densho and Jeff Froese here on the call or the workshop today. So in that aspect, we'll stay tuned. So at this point, I'm going to turn it over to Marissa and then Cam so that they can discuss the technical work we've done so far. So I'm going to hand that off to Marissa now.
Thank you. So a little bit about the records themselves. The WRA used a census type 2-page form known as Form WRA 26, or individual record, to collect demographic, educational, occupational, and biographical data about every Japanese American confined in one of the 10 WRA incarceration camps. From 1942 to April 1943, the WRA relied upon incarcerees to collect information. This information included an individual's age, birth date and birthplace, skills and hobbies, health and physical defects, weight, height, language proficiency, education, occupations, and even religion. We believe that the Bancroft may hold the only remaining set of these Form 26 records, totaling over 110,000, organized by camp in existence. So the Form 26 records are mostly typewritten, although several thousand forms have entirely handwritten responses, and you can see an example on the slide here. While these forms contain primarily structured data, there are a lot of discrepancies in data types, content, and spacing of text on the page. We've also discovered that several different versions of the forms were used. Many documents also include stamps, handwritten corrections, strike-throughs, notes, and other marginalia, which have proved challenging. And Cameron will touch on that a bit more. The data also has an interesting history. Incarcerees and other WRA office staffers coded the data from the forms to early computer punch cards during World War II, as Mary mentioned. A copy of these punch cards and the original forms were deposited at the Bancroft at the end of the war. In the 1960s, the library worked with the nascent UC Berkeley Computer Science Department to transfer those punch cards onto magnetic tape. The Office of Redress Administration, or ORA, acquired a copy of this data in 1988 to help disperse reparations to former Japanese American incarcerees. And the file was then transferred to the National Archives, who published it as part of its Access to Archival Databases project in 2003. Referred to as the Japanese American Internee Data File, it currently serves as an authoritative resource for former incarcerees, their families, and researchers. In our project, we're hoping to address some problems with the existing data file. So first, there are a number of gaps, truncations, and basic errors present in that data file. And quite a bit of information from the original forms is missing, including data about activities, skills, hobbies, educational and employment history, including information such as wages, and detailed geographic locations and addresses. So you can see here an example. None of this information from the employment history has really made it to the existing data file, which you can see in white down below. To give you an example here, another example, you can compare the top image on this slide, which is a snapshot of an individual's educational history from their record, to the bottom, which is a screenshot of what appears in the NARA data file. You'll notice that specific details about educational institutions and dates attended are missing, and the educational history has been coded to represent only the highest grade level completed. So we're hoping that by applying a machine learning pipeline, it can help us to recover more information from the original paper records and produce a richer and more granular data set than the one currently available. So I'll briefly just walk you through the project's major components and then turn it over to Kim to talk about the more technical aspects. So the original forms are first sent to our offsite vendor, Backstage Library Works, for digitization. And in return, we receive preservation copy TIFF files, access copy PDFs, and OCR text files that are reviewed for quality and completeness. Once we have the digitized files, we can begin to apply a trained, customized model to read and extract data from these images. So leading up to a pilot project with the set of Form 26 records from Topaz, the library worked with Doxie.AI to establish a working data model, which mapped regions of the documents to specific fields and types of data outputs. We've also made many discoveries about the content and structure of the form, of the data in the Forms 26 records, prompting additional collaboration between library staff and Doxie to integrate new observations about the records into the pipeline as we go. Due to variability in structure, content, and other unique characteristics of the physical records, we've adopted an iterative approach which handles sets of Form 26 records one camp at a time. Once initial test results are inspected and improved by both Doxie and Bancroft, the pipeline is temporarily frozen in its current state, and Doxie runs all of the files associated with one camp through their customized OCR pipeline, which Cameron will discuss further. Doxie then uploads extracted data in CSV and JSON formats to a shared private GitHub repository with some personally identifiable information, such as social security numbers, already redacted. Bancroft library staff provides feedback on results and notes areas for improvement in preparation for the next camp. So it's always iterative. Our next steps will include cleaning and attempting to normalize the data using tools like OpenRefine. With help from our community partner, Densho, we'll be working with the community advisory group to help us think through potential ethical issues. in regards to providing access both to the data and the digitized forms themselves, and to establish policies and practices that are informed by community concerns. And finally, we hope to publish the data and accompanying documentation in a public GitHub repository, and access copies of the digitized forms will, if deemed appropriate, be made available on Berkeley's digital collections platform. And now I'll hand it over to Cameron.
Thank you, Marissa. And thank you. Just want to start with a thank you to the Bancroft team for involving Doxie in this project, as it's been our founding project, and it's one that we find to be quite valuable and impactful to society. And so to start with, I just want to begin with talking about why customizing a pipeline is important. And in the center of the screen, we were founded out of UC Berkeley's iSchool. So we're data scientists by trade. One of the first things they teach you is that if you just take stats and coding, you have machine learning. And that's what you'll find with standard models in the market today, if you were to go to a large vendor and grab one of their models off the shelf. This can be very helpful because it provides a lift very quickly. The challenge is that without taking into account the domain in which you're working in, you can run into inaccuracies. You can inadvertently mishandle sensitive data or not understand unique fields that are present in the data that you're analyzing. And so one of the reasons why we really believe in this partnership with Bancroft is because we're able to share their domain expertise with our machine learning expertise. And so with these forms, we look at this at a field by field accuracy metric. And so some of the reasons that's really valuable is with the pre-processing of the data. So when you're analyzing the data with OCR, the binarization that's happening is quite important. On these documents, the fading changes depending on where on a given document you're looking at, and document by document. And so one of the things that we discovered is that by binarizing on a much more localized level, you improve the OCR results quite significantly. You're able to put into place sensitive data protocols. Our QC process has uncovered a lot of uniqueness about different forms that we wouldn't have found otherwise. And so this sort of iterative back and forth approach to developing a custom pipeline has been really valuable and unlocked a lot of great findings. And of course, we're doing this in a resource constrained environment. And so our end goal is to save time and cost with achieving the results of these projects. So if you want to go to that next slide there. So the Doxie.AI's process is, we start with the baseline models, and really most of these are going to be open source models, Tesseract, OpenCV, et cetera. And we're going to start with some data exploration to say, without domain expertise, how do we understand the images that we're looking at, and how would we segment the data? And then we go into we run some basic models across the data, and we look at those results, and we start finding artifacts within those that we don't understand, that we want clarity on. And then that's where the partnership with Bancroft has been incredibly valuable, is this sort of iterative middle section. So we take this process and identify the information, bring it back to Bancroft, say, hey, we're seeing this. Do you understand it? Then they provide their input, and we start iterating on this until we find a pipeline that is going to work for the data. And once we're comfortable with that, we run the rest of the documents. Doing this camp by camp has actually demonstrated a really vital need around this as well, which is these documents were not made to be read by computers. They were made to be read by humans. And so what you find is in each camp, humans made different decisions. And so one camp has slightly different orientation of the stamp or slightly different sizing on the paper. One camp has text, like pure handwriting, because maybe they didn't have a typewriter. Each one of those camps has required customization. And as we develop the learnings that go along, we'll propagate those back at the end across them, hopefully to provide Bancroft with all of the learnings we've had along the way. So anyways, it's a key piece there of, when you try to take a standardized approach across historical documents, it's a real challenge, as I think some of the conversation earlier highlighted. but Marissa, if you go to the next slide here, I wanted to make some of the findings, some of the approaches a little bit more tangible for you all. So this is an example of some of the post-processing. With an unstructured document, when you have a paragraph, you have the context, as the last presentation was showing, that the models can learn off of. With a structured document like this, each part of the document becomes the context you have to approach. So every field on this document has customized pre and post processing applied to it. In this case, we're knowing to expect characters. So when the machine learning model returns integers and symbols within there, we have a post-processing technique to be able to then return that back to an expected string. There's other fields on there that, when with age, for example, if age and date of birth conflict, we can put in a flag to request, a reviewer to look at that field. So there's benefits to the structure of this document that we certainly try to take advantage of. And if you go to the next one as well, there's one more clear example of developments that have happened over time. So in the market, there aren't really like standard models that without customization would understand checkboxes in this form. When we initially took on this project, we were focusing on identifying, is this square that you see on this, so next to married, is that squared filled in enough to be able to identify that as checked? And if it was filled in enough, we'd identify it as checked. Due to smudges, we actually had a lot of false positives in that situation. And so we developed a deep learning model to identify where the checks are, where these crosses are, and then from there identified the closest box to it. And that has significantly improved our results. And so these are the types of improvements that over time we're iterating on and sharing back with Bancroft. Also, as a note for the overall group, when you look at our baseline models, we start at honestly about 50% accuracy. And after pre-processing, you see that go up to around 80%. And then when you add post-processing in there, that's when you see about up to 90 to 95% accuracy on average. And so really most of the lift is not necessarily around custom modeling, but it's around identifying, looking at the data, and then understanding the pre and post processing required to get to the most accurate results that you're looking for. So if you go to that next slide, just to make things a little bit more real, for ourselves, we look at this as structured data, which means it's ready to query, ready to ask questions of, it's ready for research, but we know that there's a lot of additional questions that need to be answered about what truly makes data ready for research. When we looked at every single one of these fields, over 90% of them far exceeded the expected results, which we felt was very positive. And then when doing the math in terms of 110,000 of these forms, front and back, hand annotating those would take over 13 years of labor. And that is really untenable in terms of time and resources. It's quite hard to find that. And so with Doxie, we've been able to shorten that timeline quite significantly. And lastly, providing additional flags for expected errors is a big value add in that next stage of the pipeline. So at this point, I'll turn it back over to Bancroft to talk about lessons learned.
I think that's me. So thank you, Marissa and Cameron. So we'd like to conclude by sharing a few observations that we've made so far in this process. The success of the project to date has been built largely on leveraging partnerships that bring together technical expertise with content and domain expertise, as well as eventually community knowledge in the spring. So developing the pipeline with Doxie, creating a plan to clean, normalize, and prepare the data set for publication, and eventually applying a responsible and ethical framework for co-curation of digital archives held by Bancroft in collaboration with community stakeholders are all iterative and collaborative processes, and certainly represent models that we hope to implement in future projects as we scale this work up. Importantly, the costs and scalability of machine learning for other collections is a major consideration. How are we going to apply machine learning to our other collections? So finding records that would benefit most from this process depends on a variety of factors, such as the structure and content of the material, the size and quantity of a collection, and the consistency of the records, which is something we found. We thought we had a very consistent project data set, but we did not. So applying machine learning is not a one-size-fits-all approach, but rather represents a compelling and efficient and cost-effective method that we can employ as we look to extract data from our other archival holdings. We'll continue to explore this question of how far we should go in creating a research-ready collection, but it's not a matter of if, but rather how far we will go in using machine learning in our archival work. And in the course of this project, we've learned a great deal, but as I've noted, we have a way to go still, and we look forward to connecting with other projects as we continue to pursue these questions. And we appreciate very much being a part of this workshop. It's our very first, and I've been following Richard's work for a while, so this is great to be here. So we appreciate your time, and please let us know if we have any questions.